So record is independent of YouTube and record both?
Yeah, it is two independent things. Okay, so welcome everybody to Integrability Journal Club. And today I'm very happy to introduce Vladimir Korepi from Stony Brook University, who will tell us about Lattice nonlinear Schroedinger from history to open problems. Please, Vladimir.
Thank you very much for inviting me. It's a privilege. So nonlinear Schroedinger is one-dimensional non-relativistic model. So X is one dimension. I integrate here. In classical case, psi is a complex function and dagger means complex conjugation. In quantum case, Poisson brackets will be replaced by commutator, and this will be kinetic energy, non-relativistic. So energy will be square of momentum plus kappa. Kappa is coupling constant, positive in this. In this case, and in quantum case, this will point-like interaction. But even in classical case, the model is completely integrable. It has Lax representation and infinitely many conservation laws. And it's explained. There is a book by Fadiev Takhtajan, and it's explained, everything explained there. So we're going to discretize X. So instead of continuous X, we shall introduce N, which is integer number, and delta lattice step. And that's Lax representation on the lattice. I mean, time is still continuous, but space became discrete, and that's the way Lax representation looks on the lattice. So let's go to quantum case. In quantum case, Lax representation actually follow from Yang-Baxter equation. I will, this PDF file, I will send it to organizing committee, and the links are clickable, meaning that if you click on this link, then the paper will open up in your browser. So in quantum case, Lax representation follow from Yang-Baxter, and our matrix for nonlinear Schroedinger was known long before, and actually our matrix by itself was found by Yang, Chen-Lin Yang himself, 1968. I think this is the first ever R matrix. This is 1 plus permutation, lambda and mu spectral parameter. Well, later we shall use the fact that at special values of spectral parameter, our matrix turned into one-dimensional projector, so it will be important due to some reasons later. As for the questions, I would like to classify questions for two categories. If you have a short question about notation, please ask during the lecture. You can unmute yourself and ask the question. If you have like a longer question, more like philosophical nature, maybe that's in the end. If you ask the question, maybe it will be nice if you unmute yourself and also show your video, maybe say your name. Okay, that's so much for the question. Okay, so let's proceed. Oops. Okay, so this is L operator on this dense lattice when the delta lattice stop is relatively small. Jumps. So Fadiev, Takhtajan, and Sklyanin, they formulated algebraic Bethe ansatz. L operator looks like this: lambda is spectral parameter, delta lattice step. This chi is a rescaled quantum field. I will use it for a while later. So psi multiplied by delta, it will appear in some other transparencies. There is it's a correct expression valid up to delta square, and this is commutation relation. Well, quantum inverse scattering method. So later, together with Zergin, we kind of found out all of those high corrections in delta. In lattice step, there is like in Taylor series, we sum it up, and this is exact lattice L operator for nonlinear Schroedinger. Our matrix is the same. We didn't change our matrix. Our matrix is Young R matrix, 1 plus permutation. L operator look like this. So by now I have this psi dagger sign, number of particles on the diagonal, and rho is a square root, and I have this number of particles under the square root. So that's exact in the sense that's exactly on the lattice. So I can take this L operator, lattice L operator, multiply by sigma z power matrix from the left, and then this will turn into the L operator of XXX. But so meaning that I can write L operator is identical multiplied by spectral parameter. I is the square root of -1, of course. And then the matrix I decompose into power matrix, and the coefficients are these operators. And they form a representation of SU2 algebra with a negative spin, -2 divided by kappa delta, coupling constant and lattice spin. Main example will be S equal to -1. So this lattice nonlinear Schrödinger is also XXX with negative spin. So monodromy matrix is central object of quantum inverse scattering method. I multiply these L operators, get monodromy matrix ABCD is a standard notation for entries. They're quantum operators, of course. The trace of density matrix is a central thing because Hamiltonian can be extracted from the trace and high conservation laws. It has a commutation relation given by the same R matrix like L operator. And then it's easy to invert. So to invert, one can basically use some simple generalization of Kramer formula. This is just basically Kramer formula up to the shift of the spectral parameter. And the determinant also kind of a ABCD, like classical case, but with the shift of the spectral parameter, and the shift explained by that fact, which I mentioned before, that when lambda minus mu equal to I, square root of -1, our matrix turned into one-dimensional projector. So this is inversion and quantum determinant. They call the antipode in quantum groups. Okay, L operator. How about Hamiltonian? Hamiltonian was constructed by Tarasov, Faddeev, Takhtajan, and it describes interaction of nearest neighbors. Hamiltonian can be written in terms of psi, logarithmic derivative of gamma function, and the argument J is solution of this quadratic equation. But in this quadratic equation, everything commutes. So I can use Viet formula and with a square root and then put it in, and that will be expression of this Hamiltonian LNS. This Hamiltonian also appears in high energy physics. It describes the deep inelastic scattering of an electron on a nucleon. So let me say a couple of introductory words about this. So Lev Lipatov considered small Bjorken X, and in the limit of large number of colors, he described interaction of energized gluons by this XXX Hamiltonian. In other words, the scattering of a lepton on a hadron, the sum of Feynman diagrams in leading logarithmic approximation. Later diagrams dominate. Quark exchange gluons, the Hamiltonian of lattice nonlinear Schrödinger, this Faddeev, Tarasov, Takhtajan, describe interaction of the gluons in here. And then this is constituent quarks, and this is a photon which was emitted by this electron, virtual photon. So that's the picture. Lepton, which is electron, hadron, virtual photon interacting with one of the quarks. We can in here, let's consider, I might consider semi-classical approximation for this virtual photon. I come into the first open problem, which is, the spread of the entropy inside of the hadron. So first of all, let me mention that inside of the hadron, of course, there is some kind of a soup of quarks and gluons, and the signal spreads through this distribution of quarks and gluons in the lepton with a velocity smaller than velocity of light. So on the other hand, also the size, the physical size of this virtual photon is much smaller than the size of the baryon. So when the photon gamma star spread goes through the hadron, it causes a shockwave. It causes a shockwave in semi-classical approximation. And then the volume of this Cherenkov radiation, that's a gamma photon, the Cherenkov radiation, the volume increase as a cubic function of time. So first open problems describe the time evolution of entropy while the virtual photon cut through the hadron. Is this cubic in time? I mean, this was semi-classical approximation previous. Okay, so this is an important problem. It can be compared to experimental data. Here in DAISY was decommissioned, but still there are data which will be analyzed sooner or later. So deep inelastic scattering is important for experiments. So let's return back to lattice nonlinear Schrödinger. Lattice nonlinear Schrödinger has Bethe ansatz equation. This is Bethe ansatz equation, which looks exactly like XXX with spin -1. So this is just general spin, and this is a substitute -1. But and that's, this is a system of equations. So many equations, and that's the energy of that Hamiltonian. And here I have supposed to substitute the solution of this equation.
Sorry, what is spin -1?
Spin -1. The Heisenberg Hamiltonian exists for several different spins. And originally Heisenberg himself introduced spin 1/2, and there was later generalization for positive integer and half integer. And what I'm talking about is generalization of Heisenberg Hamiltonian for other real values of spin, and specifically spin -1. This, are you happy, Sergei Pirogov?
Yes, yes. It is infinite dimension. What is the presentation? What representation of?
It was in the first transparency. Remember in the beginning. Here's the representation. Here is kappa is Bose field, right? This is Holstein-Primakov. Kappa is Bose field. Rho is square root, and this it's Holstein-Primakov. So I wrote in terms of harmonic oscillator, Bose field on the lattice. This is representation of SU2 of this spin.
And the rho, what is rho?
What is rho? You missed completely the beginning of the lecture. Here's the rho.
Thank you. And chi is a Bose field, yes?
Wait. See commutation relation, chi prima equals delta is a number.
Bose field. I see.
So I come back.
Thank you.
Of course.
Thank you.
Of course.
Maybe one small comment about spin in this in BFK's story, Lipatov story. It is originally S equals 0, yes, and then in this Fadeev-Karchemsky, they did similarity transformation to S-1.
There is some transformation, and also there are several publications. I mean, Kozakov and Gromov published something about XXX with negative spin. He's just here in attending right now lecture. So I mean, experts know about this XXX -1. Gromov published a paper. I mean, there is a reference. Wait.
He's not just.
It was somewhere. Wait, let me dig here. Kozakov, Zaremba, Gromov, Kozakov. See?
Yeah, just to confirm, negative spin is a legit thing.
Legit, right. Thanks.
Can I say a word? Hello.
Hello. I mean, I permit you, but I'm not the chairman. You should ask the chairman.
Yes, thank you. I think the easiest explanation is that S equal to -1 corresponds to representation of the group SU11.
SU11.
Yeah. Hyperbolic rotations instead of SU2S for usual values of spin.
Thank you, Zhenis.
Okay.
Thank you.
So can I move?
Yes.
Okay, so let me find the transparency where I was. Okay, this is yeah. So this was first open problem we pass. So XXX, Bethe ansatz equations, and then this is system of equations, so it should be valid for any k. This kind of each equation kind of associated with one specific lambda k, right? Number of equations coincide with number of unknown variables lambda. That's the energy of that Hamiltonian of Fadeev-Tarasov eigenvalue. Okay, so a Bethe ansatz equation. Let's prove first theorem. Only real if solutions exist of Bethe ansatz equation, then all of them are real numbers. How I can possibly prove this? First of all, let's study the properties of the factors. Well, here, this is the properties of the factors. This is really trivial. I don't want to waste time. This is correct, believe me. Okay, so let's have in mind these properties of these factors. Let's prove, okay, so let's prove that if solutions lambda exist, then all of them are real numbers. So how I do that? First of all, I choose one of the lambdas with the maximal value of the imaginary part. So far, I didn't prove that imaginary is 0. I'm going to prove it, but before I prove it, I assume there is some imaginary part. So let's take the maximum. If there's several of lambda with the same maximal, I take one of them. So let's pick corresponding equation corresponding to this maximum here. So since it's maximum in the right-hand side, imaginary part of this difference will be positive. So the right-hand side will have a modulus magnitude greater than 1. But the left-hand side, when I look in the left-hand side, I understand that this thing is greater than 1. So if it's greater than 1, means that imaginary part of this maximum is smaller than 0 or equal. So, but this was maximum. So all of them has negative imaginary part. Okay. This is first step of the proof. Second step of the proof, I can choose a minimum, lambda with a minimum imaginary part. Repeat all of these calculations and then prove that all imaginary parts are positive. So that's a proof. So this means that imaginary part of each and every individual lambda is equal to 0. That's a proof. So I finished the proof of the theorem that all solutions, if exist, then they are real numbers. Okay, I proceed to the next. Oops. Okay, so let's take a logarithmic form. More usual form of Bethe equation is a logarithm. First of all, I want to mention that some time ago I proved Pauli principle. Pauli principle means the following. So all lambdas, I mean, there is formulas of algebraic Bethe, which Professor Sklenin discovered. And this is like B, all lambdas inside of B has to be different. So we studied this case when two lambdas coincide, I get B squared. There is no such wave function. It doesn't exist. So Pauli principle. All lambdas are different, but then this also means that all n's are different. So this integer or
I have a notation question. So your logarithm, is it standard branch logarithm or it's actually arctange?
This is standard. What theta is equal to I. Standard logarithm ik plus lambda is ik minus m. This is standard normal usual logarithm.
Because in this case, mod numbers can be equal, right?
Well, if two n's equal, then two lambdas equal, and then there is no such wave function. So, I mean, I can send you, the PDF file, click, that's the paper we prove it. It's also in my book. Last time I sent you the book. In my book, there is a chapter which is called Pauli principle. Do you want me to see?
If log is standard branch of log, then mod numbers can be equal and solution still not trivial.
See, the log chosen the following way. When lambda equal to 0, then log is equal to 0.
All
so
right.
it's anti-symmetric function. And then, if two n's are equal, then two lambdas are equal, and this is forbidden by Pauli principle. You want me to send the link to this paper? It's also in the book. Okay, we can discuss this later, but Pauli principle will appear several times. Okay, so I proceed. Okay, so Pauli principle will appear many times. So this Bethe equation, they have a part of this action, Young action. So this is Young action. Theta 1 is the integral of theta of the scattering phase, which was on the previous transparencies, theta 1 of differences, and this is integer numbers and lambdas. So Bethe equation, which appeared on the previous logarithmic form, extremal points of this S, ds d lambda equal to 0, then this is Bethe equation. So this is matrix of the second derivatives of this Young action. And the K is, K was somewhere in the previous transparencies. Yeah, here is K. Kappa is coupling and lambda minus mu squared. Okay, so meaning that K is positive. So let's calculate the quadratic form of this matrix. So I can separate this contribution, which is LKV squared, and then one given K, like lambda 1, lambda 2, appears actually 4 times in the matrix, and all of this can be compared and combined into this quadratic form, the difference of the vector square multiplied by K. So positive quadratic form, meaning that all the eigenvalues of this matrix of secondary positive, the S is convex, Young action is convex, the unique minimum. So this means that Young Bethe equations exist, solution exists, and uniquely defined by that set of integers, of this set of integers. So nice. So this matrix of second derivative also appear later in the series. So the square of the norm of that wave function is determinant of this matrix. This formula was conjectured by Godin in the continuous case of nonlinear Schroedinger. I proved this in 1982. The proof also works on the lattice. That's a link. If you click on this, then the paper will come out. So let's go to thermodynamic limit. Thermodynamic limit. So once again, so thermodynamic limit of Bethe ansatz described by linear integral equation. So that's a linear integral equation for the distribution of lambdas in the ground state. So rho is defined like L, length of the box, and the difference of lambda. This difference never vanishes because of that Pauli principle. So the difference never vanishes for positive value of coupling constant. The Pauli principle valid. On the other hand, if coupling constant equal to 0, then it dies. I mean, Pauli principle dies. So Fermi sphere is describing ground state for positive kappa, but for 0 kappa, it collapses. So mathematically, this means that this equation will have a singularity when kappa, coupling constant, go to 0. And that's an open problem, how to study analytical behavior of solution of this integral equation when kappa, coupling constant, go to 0. So something is known along these lines. First of all, for the continuous nonlinear Schroedinger, integral equation is similar, but instead of k, we have 1 in here. This is famous Lieb-Liniger equation. It was studied. I mean, in general, solution exists, but it was even studied this singularity when coupling constant go to 0. It was studied. The kernel, by the way, go to the delta function by that time, and I immediately see the problem, because if I replace naively kernel by delta function, that the integral will cancel the left-hand side. I'll have like 0 equal to 1, which is not good. But the limit when coupling constant go to 0 was studied in the literature. Prohak, Lang, Tracy Widom, and then they found the asymptotical decomposition of solution for small kappa. And this is a Taylor series, it's square root of kappa, log kappa, with the coefficients which are noble objects of the number theory, like Riemann zeta 5 or something. Okay, so open problem. We proceed. So now, let me close here. Okay, so return to the latest case. Continuous limit. We continue our study of thermodynamic limit. That was the energy on the for the finite volume when we have this system of Bethe ansatz equation. In thermodynamic limit, everything simplifies. So rho distribution of lambdas in the ground state we discussed, but there is also excited state. All excited states can be classified in thermodynamic limit. Means there is only one elementary particle. One elementary particle has energy which is described by this equation. So this is so-called bare energy, this expression. And this is integral k I already wrote. So this integral equation, I cannot solve it analytically, but I can prove the solution exists unique. And this describes the energy of elementary excitation. By the way, epsilon has to vanish at the edges. I mean, there is explicit construction of this elementary excitation, and I have to break periodic boundary conditions in order to construct elementary excitation. So elementary excitation fit only into anti-periodic boundary conditions. So it has a topological charge. Oops. So that's this.
The energy spectrum, the energy spectrum and excitations are different quantities.
Energy. This was energy levels in the finite volume, the infinite volume, the ground state. Huh?
Yes, okay, I see.
The energy, there is ground state and there is excitations, but all excitations are scattering states of one elementary particle. This one elementary particle can have different momenta, and then moment will appear in a moment. So, I mean, lambda is kind of related to momenta, and then this elementary excitation, elementary particle, has energy, momentum, and also topological charge, and momentum will come up momentarily. So
EH is ground state, or what is EH? This
H is chemical potential. Chemical potential.
And energy spectrum becomes what becomes? It is one quantity, or it is spectrum? EH becomes
energy becomes in thermodynamic limit.
This one is an energy of what state?
No. I understand. Sorry for the typo. So sorry for the typo. So this energy is energy level in the finite volume. But when the
average
becomes means thermodynamic limit, when the length of the box and n goes to infinity, then it becomes this. So it becomes related, actually misplaced. I'm sorry, I misplaced it. The word becomes related to, it describes integral equation. So this is description of this thermodynamic limit when the length of the box and number of particles both go to infinity.
No, I understand. I don't understand what this E capital H infinite volume is an energy of ground state, or what is that energy? EH.
Where is
First,
E
yes.
sub H is any energy of level, ground state.
Any, but
any.
It depends on lambda, yes? Or it depends on what? What is parameter? Which
Well,
parameter?
the lambda explicitly, you have to plug here this lambda are solution Bethe equation. You have to plug them in here.
But it's unique. It is unique. Solution is unique.
The ground state is unique, but
ground. It is depend on n. I see. It depends on n.
Energy level, but also there are many different solutions of Bethe equations, right?
Thank you. I understand. Thank you.
So I proceed.
Yes, I understand.
Okay, so this thermodynamic limit means that the total length of the lattice is infinite, number of particles is infinite, but the density is finite. So n, number of particles divided by L, length of the box, is finite. Okay, so that's a picture. Lambda, spectral parameter. I mean, eventually I will write momentum of the particle as a function of spectral parameter energy. And this is my ground state, actually, the Fermi sphere. So everything here filled with particles. And the particles has Pauli principle, meaning that the only one excitation which I can make here, I can make a hole. So it's like a hole, but outside of, so this Q is like ultraviolet cutoff in quantum field theory. So outside of the Fermi sphere or Dirac sea, I can put a particle. So when I combine the particle with hole, this is my elementary excitation, which is, well, elementary excitation. So that's a momentum of this elementary excitation. When it's when lambda is large and it's a particle, then I can express momentum in terms of lambda. So everything was expressed in terms of lambda, but lambda is somewhat formal mathematical parameter, spectral parameter, and then physical momentum, which is related to the shift. For the particle is given by this, and for the whole it's given by similar expression with a minus sign. This is very standard for Bethe ansatz. Now, scattering matrix. I can consider two elementary excitations and consider scattering matrix. There is only transition, no reflection. Scattering matrix is the pure phase. I mean, logarithm of the scattering matrix is the phase. And this phi also given by the similar integral equation. I mean, in Bethe ansatz at zero temperature, everything given by similar integral equation. The same kernel of integration. This is my physical scattering phase, and this theta is bare scattering phase. This is logarithm which at lambda equal to 0, which is anti-symmetric function of lambda. So this was bare from the wave function, which I look in the wave function, I see that. And this is dressing because of the polarization correction, radiative correction. So remark, many body, this is two-body scattering matrix. Many-body scattering matrix is a product of the pairwise scattering matrices. And this can be taken as a definition of complete integrability in many-body quantum mechanics. Remark. Okay. So this was the end of zero temperature. So at zero temperature, we discussed, so this was Bethe ansatz solution of this lattice nonlinear Schroedinger for zero temperature. Now thermodynamics. Thermodynamics is described by Young-Young equation. So this is an equation for epsilon. This is nonlinear integral equation. See this log epsilon. TBA, I think hundreds of people know this as a TBA equation. And then this inhomogeneous term is different from the continuous case. In the continuous case, it was lambda square. So epsilon formally introduces a ratio of the density of the holes by the density of the particle. But still, because of the infinitely many conservation laws, stable particles exist even at positive temperature. And epsilon has a meaning of the energy of this stable particle. The open problem is still the same. I mean, when the coupling constant kappa goes to 0, my kernel of integration turns into the delta function, so I can take the integral. And then would be interesting to describe analytically behavior of solution of this equation in the limit of weak coupling. It's supposed to be singularity, it's supposed to be smaller, less severe, because thermal fluctuation kind of smoothen quantum fluctuations. Anyway, thermodynamics. So thermodynamics, free energy, we can express in terms of this solution of this Young-Young equation, nonlinear equation of the previous frame. The pressure, similar equation, and this K K is logarithmic derivative of the scattering matrix. So some people call it scattering matrix representation of thermodynamics. Also, thermal entropy can be calculated through this function epsilon. So maybe I should mention about experimental work. Amsterdam is not that far from London. And then there is a famous experimentalist von Druten. I think he has 2 dots above his U, so sorry for that. So he's experimentalist, he worked on optical lattices, he built up nonlinear Schroedinger and checked Young thermodynamics, but in the continuous case. So experimentally confirmed thermodynamics. Now zero temperature. Let's come back to zero temperature. So zero temperature, the ground state is unique. So the entropy of the whole ground state is 0. On the other hand, if I take a block of X sequential lattice sites, then the entropy of this interval of this block is non-zero. And this entropy, I mean, von Neumann entropy. I mean, the density matrix is described like this. I take a projector of the ground state and I'm supposed to trace a weight environment that's all the lattice sites outside of that block of X sequential spins. So the density matrix, I calculate von Neumann entropy. The result is a very complicated function of X, size of the block, but for large X, it scales logarithmically. 1/3 log X, this is famous formula by now, and it's the same like in the continuous nonlinear Schroedinger. So it's simple, but I make a remark. So this logarithm works many places, but not completely universal. There is some spin chains where entropy scales at the power law of X. There is some, if you click on this, I will send it after the lecture, the PDF file, then there is some spin chains when the entropy behaves the square root of X or linear function of X. So rarely, but it's broken sometimes. Now, Rényi entropy. Rényi entropy defined like this. I take this density matrix of the block of spins, raising some fractional power, alpha, positive parameter, new parameter was absent before, just new parameter, just introducing. Trace of this matrix is called the zeta function of the matrix. Logarithm 1 minus alpha. So Rényi entropy, also important characteristic of the ground state. So I'm calculating Rényi entropy of that block of X size. So for large X, it also scales logarithmically, coefficient dependent on alpha. And it's the same also usual formula, which is very well known. It's the same like XXX. Note, so in many models, Rényi entropy is analytical function of alpha. Actually, in many models, this is this function of alpha, meaning there's a simple pole. But not always. There are some counterexamples. Sometimes Rényi entropy is not analytical function of alpha, meaning that the entropy scales differently for different values of alpha. This is well-known Stokes phenomena, but it actually happens in some simple spin chains. So entropy. Now, open problem. Open problem. So far, I was talking only about stationary nonlinear Schroedinger. So we was solving time-independent Schroedinger equation. We was diagonalizing Hamiltonian. It's more interesting to study time-dependent Schroedinger equation, time evolution. There is a lot of publications. It's a very popular subject. Many people publish. And one of these approaches, which is described here, should work for lattice nonlinear Schrödinger. But so far, time evolution is an open problem in lattice nonlinear Schrödinger. Correlation functions and XXX, open problem. So for XXX with spin 1/2, we know that all correlation functions are polynomial with rational coefficients of the values of Riemann zeta with odd arguments. These values of Riemann zeta and odd arguments, this is celebrated object of number theory. Apéry studied them, and then they're conjectured to be transcendental numbers, algebraically independent over the field of rational numbers. So once again, for spin 1/2, correlation functions are polynomials of Riemann zeta with rational coefficients, but this it was for spin 1/2. For negative spin, spin -1, the one which I study, correlations once not studied that, but maybe they can also be described by number theory somehow. It's unknown. It's open problem. Proceed to the next open problem. So next open problem. For the XXX spin 1/2, for the XX spin 1/2 in thermodynamic limit, very long lattice size, there is additional symmetry arise. This is Young's symmetry for the infinite spin chain. This similar symmetry, Young's symmetry, also arises in a Hubbard model, one-dimensional model. So also recently in quantum field theory, these Young's symmetries are very important. Bizert, Staudaher wrote papers about Young's symmetry of supersymmetric Young-Milson 4-dimension. So the open problem is, let's come back to our x-axis with negative spin. Maybe some new symmetry arises in the thermodynamic limit of the infinitely long lattice. That's an open problem. Now, for the time, let's have a break with open problem. Let's make remarks. So the whole lecture, my whole lecture is devoted to lattice nonlinear Schroedinger. There is another discretization of lattice nonlinear Schroedinger. The one which I described for myself, I call Isargin-Korepin version. There is another discretization, which is called Ablovitz logic. Ablovitz is famous American mathematician from the Midwest of US. So Ablovitz logic, they wrote it in, that's a classical case. So n is length, well, it's this lattice side, right? And time is still continuous. So there, Ablovitz logic, very simple looking. It's completely integrable. It has L operator and another discretization of lattice nonlinear Schroedinger. But then Tim Hoffman, he's a professor of the Technical University in Berlin. He proved that Ablovitz logic is gauge invariant to the version which I'm explaining, to this Isargin-Korepin version which I'm explaining. So gauge invariant of gauge transformation of the transfer matrix, this ABCD thing. So this is kind of nice and somewhat non-trivial, but on the classical level, they gauge invariant. On quantum, there are some complications, but I will comment quantum only if there will be any questions. Now, another note of the classical Ablovitz logic. Classical Ablovitz logic has important application. For example, classical Ablovitz logic describes quantum correlation function in a spin chain. That's a link. If you click onto here, then you will see in some spin chain, XX, 2 x's. The classical Ablovitz logic describe correlation function, quantum correlation. Okay. So right now, let me recall the beginning of the lecture, because the lecture was called lattice nonlinear Schroedinger. But so far, only space variable was discrete. How about time variable? Time variable also can be discretized. And people work on this. Tim Hoffman, the same Tim Hoffman, wrote a paper about the double discrete nonlinear Schroedinger. He arrived to this from the point of view, his main application was geometry. And he wrote it, that's a link. If you click into here, then the paper of Tim Hoffman will come up. So his nonlinear Schroedinger looks like a bunch of recursion relations, which are in this paper. But the solution of his double discrete nonlinear Schroedinger is nice. It's called Hashimoto surface. That's a Hashimoto surface, the right one. So this is a straight line and an angle. Hashimoto surface is completely integrable geometry. So modern way to describe this is tropical geometry. Volkov work on this, Sasha Volkov. And then they have application. Actually, it has application to architecture. Architects build building out of this. So this field of double discrete, completely integrable equations was developed further by Alexander Bobenko and Yuri Suris. They're also in the same Berlin University. They wrote a book. You click, you get to the book. So this brings us to an open problem, because Bobenko and Suris wrote that book, and Hoffman wrote double discrete nonlinear Schroedinger, but all of this was on the classical level. How I can quantize double discrete, discrete time? This seems to be a problem because, it's open problem formally, but I think maybe it can be solved by means of Taylor series. What I'm trying to say that when time is discrete, I don't have Poisson brackets. I don't have Hamiltonian formulation at all. So I don't know how to quantize, but maybe I should use Taylor series. Maybe this time step. Maybe I should decompose everything in the time step in the Taylor series of the time step. So the lowest order in the time step of everything, of the whole construction of Tim Hoffman, will correspond to the continuous time. In the continuous time, I will have a Poisson brackets and Hamiltonian, and then I will replace my Poisson brackets by commutator and quantize. As for the higher orders of Taylor series and the Taylor series, maybe I will be able, or you will be able to restore them from the requirement of quantum integrability. So
sorry, I'm a bit worried. So this password you provided, will we not be sued by Stony Brook for posting it on YouTube?
Say again?
The password you added, will we get some legal problems with Stony Brook after posting it on YouTube?
I use the password. Okay, let me tell about the password. So I received the email from Zhenya Sobko, and there was this link and the password, some GGG. And then I use that password. I didn't introduce any new passwords. I used the password which was provided to me by Dr. Eugene Sobko.
No. The last link to the book on this slide.
Ah, the last. Just, you
Stony
know.
Brook, blah, 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 and then password.
Ah, right. Blah, 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 blah. You know what? I'll explain to you, blah, blah, blah. Ah, this password. Okay. So listen carefully to my answer. So this link, no, you will be able to go through. So this is a lecture of Dennis Sullivan. You know, Dennis Sullivan, a famous mathematician of Stony Brook University. It's video recorded. It's in Stony Brook. You know, there's a video recording library of the Simon Center for Geometry and Physics. And that's a link to there. You just click the link and use this password. Or otherwise you can use a search for Dennis Sullivan.
So there is no legal protection to the...
No legal. On top of this, you know, you're in the different countries. So, you know, if somebody wants this international court in Hague, I mean, it's too complicated. Don't be...
Yeah, but America...
So no legal action. Can I proceed by now?
Yes,
please.
Professor
and by the way, we more or less in the point of coffee break. So if you
wait, I finished just in 1 minute.
Yeah. Good.
So that's the references, and that's more references, and that's all I want to say. Thank you for your attention.
Okay, thank you. Thank you. Let's thanks Vladimir for a very interesting talk.
Thank you.
Yeah.
What's the time right now? Right, so now it's 11. In principle, I mean, if there is any reason, then I can stay till noon. But I don't know. What's the plan? I mean.
So, well, I guess we can go with questions.
Well, I propose maybe we have like coffee break and have some informal discussion over that.
Wait. Coffee break means what? 15 minutes or what?
Well, I mean, we just make it and discuss a little bit more.
So coffee break is discussion, right? Coffee break is discussion. Okay. I can stay 1 hour at noon. So in 1 hour, I have to go absolutely. But this 1 hour, if there's questions, discussions, I will be glad to discuss, please.
So then let's finish the formal side. Let's thank Vladimir again, and then proceed.
Thank you.